And in Newton, of course, is a kilogram meter per second squared. So I can refine this whole business of a Tesla, and Tesla is a derived unit, and I can express it in terms of the fundamental units. Let me go back into the direction. So provided that we have the proper units in here. Before I do the directions, let me talk about the strength of the magnetic field for the Earth. The Earth has a magnetic field that is its value is actually a small value. So the magnetic field of the Earth is it ranges anywhere from 25 to about 65, so that's a range of microteslas. So 1 Tesla is a big number, okay? And the Earth's magnetic field, and the compass can tell you which way it's pointing, is a small magnetic field. In the lab, we can create 1 Tesla. We can create actually 10 Teslas. I mean, with given enough strong electromagnets, we can create super strong magnetic fields up to 20, probably 30 or more Teslas. But a Tesla itself is not a common unit really for measuring magnetic fields, because it's too much of a magnetic field. We'll be talking about tiny numbers of what a Tesla is. So instead of using a Tesla, we use the Gauss actually in a lot of places, and that term you will probably see in some of the homework problems. So I want you to make sure you're aware of what the Gauss is. When Gauss, and it's written G, so let's not confuse that with the gram, is 10 to the negative 4 Teslas. Okay, so the magnetic field can be expressed in terms of a Tesla, or in more practical units as a Gauss, because then the magnetic field for the Earth, which is, let's take a typical number that we're going to be using unless otherwise are told, is about 50 microteslas. And remember, a micro is 10 to the negative 6, so it's 50 times 10 to the negative 6, or 0.5 times 10 to the negative 4 actually, or half a Gauss. I mean, it's much easier to say half a Gauss than 50 microteslas, or 50 times 10 to the negative 6 Teslas, okay? When you talk about 1 Gauss, 10 Gausses, 3.5 Gausses, it's a more practical number. But don't forget this conversion factor in here when you're doing your problems. Let me go back into the direction, because it's very, very important that we get the direction correct, okay? Now, this is a right-hand rule. That is basically how you find the force that results from a charge moving inside a magnetic field. Usually, in the right-hand rule, if the thumb is the x-axis, the y is the index finger, and the middle finger is going to be the z-axis. I can rotate this one whichever way I want to, so I can start with this one, the x-axis, as long as I keep the direction, okay? This would be the y-axis, and this would be the z-axis. Furthermore, I can actually start here, x, this would be y, and this would be z. In other words, you have to be very careful out. This would be the z-axis in here, okay? That is fine. That follows exactly. That is an important property, because some of the books actually you will see that this one is a little bit flipped. So I don't want you to confuse that. So let's remember this property of the right hand. In other words, you can always turn right hand whichever way you do, and the thumb will always point into one direction versus the other directions as far as the forces are concerned. I mean, at least you keep it to right hand no matter which way you rotate it, and that's an important property. Okay, having said that, this is the direction of the vector v. That is the vector velocity, the velocity for of the particle. This is the direction of b. If I do that, then v cross b is going to be this vector. So that is v cross b actually, given by the right-hand rule. If q is positive, then this number, the magnetic field force, is going to be pointing in the direction of where the middle finger you're going to have it in. So you have to really remember that, because otherwise you're going to have this one backward. Now, if q is negative, okay, which is a possibility. And actually, it's a very, very plausible possibility, because that's what we deal with day in, day out, because we're going to be dealing with electrons. So if Q is negative, I need you to remember that. I need you to remember the fact that when Q is negative, if Q is less than 0, the force, I mean, we're talking about the magnetic force in here, so you have to remember that. The magnetic force points in the opposite direction. I'm writing with my finger, so I'm sorry if I don't have a. It's actually easier to write with the finger than to have to write with the mouse, actually. Okay, so it's going to be if Q is negative, the magnetic force points in the opposite direction of the one given by the right hand rule. Okay, RHR stands for the right hand rule. So this is some of the things that you need to remember. You really have to practice this one. I really want you to do that right now. I want you to open your right hand. So if you're a left-handed, it doesn't matter. You have to stick to a right hand. You start with V and then B. They don't have to be, by the way, a 90-degree angle, because you're going to take the sine of the angle between them. If they are parallel, of course, you're lucky, because then V cross B is going to be 0, or anti-parallel is going to be 0. Because sine of 0 is 0, or sine of 180 degrees is still 0. Now, if they have an angle between them, you're going to include that part of the calculation, because we're doing the cross product in here. We're not doing anything else. V cross B is going to be the third finger that you're going to produce from the cross product using your right hand. And then, depending on Q, if Q is positive, that is actually the direction of the force, the magnetic force. If Q is negative, all you have to do is, you cannot twist your arm. And it's going to be very hard to do it because it's not going to be correct. So, I mean, unless you break your finger, which you don't want to do that. Don't do that, okay? Okay. Then that's going to be the direction of the direction of the force will be opposite to that one if the charge is negative. So what it all means, let's take an example, and we're going to close with that example today. We're going to take a charge that has just entered a region of magnetic field, and it was moving. I'm going to take it moving in this direction, V, and this region of space has a magnetic field that is pointing inward. In other words, I'm going to point it like this when I'm talking about a vector that I cannot draw. Of course, it's in the entire region has this magnetic field in it, so it's not just some points in it. So the entire region has a magnetic field that is pointing inside the screen. Okay. When you see this symbol, that means the vector is pointing inside the screen. When you see this symbol, oops, I have, let me go back in here. When you see this circle and inside of it there is a dot, I keep on losing this thing in here, and there is a dot, that means that the magnetic field is actually pointing out of the board in there. Okay, so here is how that would look like. So this is out, this is in. Okay, choose a smaller size. Okay, so that's a distinction. So the way I have it in here, this region in here has a magnetic field pointing inside. Now, as the charge gets in, it's going to be subject to this magnetic force. Again, it's going to be Q. I'm going to take Q to be positive in here to make it easier for myself in here. So Q is positive. V cross B. That is going to be the magnitude of the magnetic field. I'm going to take B to be uniform. That means it's constant, and both in direction and magnitude. Okay. So using the right hand rule again, there is an easy technique in here in this program here. If I can find it, insert a, what is the insert? The draw, I guess. Yes, draw an XYZ coordinate system. Okay. If I can get it to let me move it in here. Okay, I drew it backward. Let me delete this. I don't like it. Yes, okay, this is a right-hand triangle. Anyway, right-hand rectangle, right-hand coordinate system. Okay, so from this dotted line is supposed to be the direction of the magnetic field, except that it's pointing inside the board. And so this is where B is going to be pointing inward. The particle was moving in here in this direction, so that's going to be the direction of the velocity v. The charge is positive, and they're making actually a 90-degree angle. This angle is 90 degrees, so I don't have to deal with the sine theta at all, because sine of 90 degrees is 1. Therefore, the magnetic force is going to be in this direction, so that is the direction of FB. So in this case, the charge is going to have a motion whose where the force in it is perpendicular to the velocity, and that motion from physics 1 is going to be, if you said a circular motion, you're right. Okay, and the acceleration in circular motion is v squared over r. Okay, so that is the acceleration in this case. It's a centripetal acceleration that you guys did in physics 1. Because F is perpendicular to V. That is the whole business in here, that this force is a resultant of the cross product of V with somebody else, with something else, so F must be perpendicular to V. Therefore, this motion here must be a circular motion whose acceleration is going to be V squared over R. That means that the magnitude of V does not change. What changes in this problem is its direction. So if I apply Newton's laws of motion in here for this particle, here is the acceleration, the vector acceleration. Here is the force, the magnetic force. And if I apply it in this direction and project that vector, so all it gives me is, first of all, Q times V times B times sine of 90 degrees, which I'm not going to write because it's 1, equals to mass of this particle times its acceleration, which is V squared over R. Cancel the square with the V, and from here we're going to find interesting result. First of all, that mv, which is the momentum of that particle, is equal to qrb. So think with me here for a moment. If somehow, let me go back to the situation. If somehow I know what the magnetic field is, okay? If I can find a way of finding what the magnetic field is, and if I know what the charge is, let's take it a proton, 1.6 times 10 to the negative 19 coulombs. And if I can measure where the particle would land, and I measure the curvature of this arc, so I find its arc to be somewhere in here, then I can find the momentum of the particle is that it had when it entered this region, because the momentum doesn't change, the mass doesn't change, the velocity doesn't change in magnitude. What changes in this case is the direction of the momentum. That's all. That's what the magnetic field does for you. It does not change anything in here in terms of magnitude, but changes just this expression. So this is a good technique to measuring the momentum of elementary particles, especially in collisions inside accelerators. The first nuclear accelerator actually was made using what is known as 2Ds. These are pieces of metals. This is actually they're hollow inside, where they allow for charged particle to move in and out. Okay. If I take this if I drop, so there is a region in here. Let's take the magnetic field again, pointing inside, everywhere in this region, and same thing in here. So it's pointing in the same direction. And if I take a charge, no magnetic field in the gap between them, and if I take this ends, these are conductors, these are metals, of course, and connect them to a battery in here, I can do something interesting, because from this expression, actually, let me write this expression again. V over R is equal to, what is it? QB over M. Okay? So if I take protons, for example, put them in this region, in between them and apply a voltage in here. So if I have a charged particle in here, okay, I'm sorry, let me get my marker again. If I have a charged particle in here, proton for example, because this is at a higher potential than this one, the charged particle starts moving this way. As it enters the magnetic field, remember the magnetic field does not give it more acceleration. All it does, in other words, it does not change the value of the velocity once it enters that region. It changes just direction. So there is an acceleration, but the purpose of this acceleration is just to turn the particle and make it come to the other side, back to the gap between the two D's. These are called D's. Okay, a D because it's shaped like the letter D. Two of them. Now, once the particle emerges from that region, what I'm going to do is I'm going to flip the polarity of this battery and make this battery this way. So in other words, the charge is going to fall back again into the other region. Whereas it came from with an initial velocity now, it was initially at rest, then it gained some velocity. So when it comes out, it's going to come out with that velocity. Now it's going to gain more velocity because of the fact of the conservation of the energy. 1/2 of mv squared final minus 1/2 of mv squared initial is equal to q, which is the charge, times the voltage, whatever voltage you put in between them. As the particle enters the second region, again, it's going to be flipped because everything is the same as before, except the velocity now is in the opposite direction. So it's going to turn actually in the opposite direction and emerge from the other side. The minute it emerges, I'm going to flip the polarity again. What is the rate at which I'm going to flip the polarity is actually this frequency. V over R is actually omega. If I do this flipping back and forth of the polarity, I'm going to always make sure that the particle will emerge in the other direction, falling in the electric field, gaining velocity, and then once it enters the magnetic field, it changes its orientation, then fall again inside the electric field, because there will be an electric field in here, gaining velocity because of the electric field, and the magnetic field serves just to push it back into that same region, and so on and so forth. By the time it emerges from here, where I'm going to have an opening in here, it's going to have tremendous velocity because it would have gone through this cycle several times and gained a lot of velocity. This was the first nuclear accelerator. This frequency is called the cyclotron frequency, and this is actually the cyclotron accelerator. I want to stop here. We have still more topics to talk accelerator. We're going to talk more about other items when we come in here. So this is an important expression that you probably will need for some of the homework problems. This one, and by far, this expression is going to be the most important one in terms of working your problems for right now in this chapter. Again, we're going to see you for part 2. Thank you.